Good evening, and a very warm welcome to this May Sigma meeting. And I'd like to extend a very warm welcome to all our people who've joined us from our sister clubs, and also all our Sigma members who are along with us tonight. The agenda for tonight is we've got an excellent talk on Mercury by Professor Keith Nicholson, followed by a questions and answer session with a tea break after that. And then following the break, we've got Stuart with the space news, and I'll be doing the club news tonight. Unfortunately, Pete's not able to be with us because he's got a bit of a family crisis that he's having to attend to. So we extend our thoughts to Pete at this time with what he's going through. I'd like to thank Stuart, Chris and Mick for helping me with this presentation tonight, and with Mick acting as co-host and making sure it all goes along swimmingly well. So now our speaker tonight is Professor Keith Nicholson, who's based up in Caithness and a member of Caithness Astronomy Group. Now, Keith is an internationally recognized award-winning scientist and award-winning company director, and he's now a consultant, and he's got about 30 years experience of statistical analysis and data modeling, which I guess at this time, or certainly in the last few years, we've all become aware of data modeling. So I don't know if you've been involved in that at all, though, Keith, but anyway, that's but before moving into consultancy, Chris was a professor of geochemistry and held positions in universities in Papua New Guinea, New Zealand, Denmark, and latterly in Scotland. Keith's research interests include the use of mineralogy and geochemistry and using them as fingerprints in paleo environments and planetary evolution. So it, I guess, gives him it means he's eminently qualified to speak on the subject tonight. More recently, Keith's been founded Cybersecurity Scotland, and he's a leading expert and government advisor in this field. So yeah, a very qualified speaker. So anyway, I'll hand over to you, Keith, and let you introduce your talk. Thank you very much. So.
Thanks very much, Rich. That's really good of you. And I'll just start to share my screen and do the usual exercise here. Slideshow. From the beginning. Is that okay, everyone?
That's perfect. Thank you very much, Keith.
Excellent. Thanks. Now just get this sorted out. Grand. Well, yeah, it's my pleasure to speak to you all tonight. It's you know, as Rich said, one of the things I've always been interested in, right from being well, really, as long as I can remember as a wee boy, I've always been interested in the solar system. And I'm old enough and lucky enough to have actually watched the moon landing live. And it's just been fascinating over the last few decades, just seeing the data coming back from various probes and the images from all the planets. And it's just such an exciting time that we're getting this data back, and there's more to come as well. So whilst I'm no longer really involved in a lot of the research in this area, I still do read the papers and look at the data and the modeling and determine what we could learn from the mineralogy, the geochemistry particularly, which is my interest, on what were the, how did the planets form, how did they evolve, more particularly, which is my interest, and you know, what information can we glean from some of the data we're getting back from the probes about these individual bodies and their evolution. So tonight I want to speak to you about Mercury. And this is the sort of broad area of the talk I want to give you a bit of history of discovery. Mariner 10, of course, the first probe, we'll have a look at that, and Messenger, which will form the bulk of the talk, or the data that we've got from that. And the images and the data we get give us some areas, some insights into the physical characteristics of that, the topography, the geology, tectonics, and of course the geochemistry of that. And I'll mention the current mission that's en route, but there's not much data from that yet. That's 2025 before we'll start to see data coming about from that. So just by way of introduction, Mercury, of course, is one of the 5 visible planets, been known since, well, since the ancients, really, in ancient cultures, all recognize Mercury. And you'll see here on the slide, the different nations have given different names to Mercury, and sometimes the morning and evening appearances of Mercury receive different names. But the key thing really is that it's always been observed, and it's always been recognized as one of the fast-moving planets, and that reflects its name. On this slide, and you'll see quite a few other slides, I've put quite a bit of text, not to go through it tonight, but so when you look at the slides later, there's more information than just what I talk about in the next 45 minutes or so. So there's a bit more insight for you there. And the different names of the planets from different cultures, I think are really quite fascinating. But if we start to look at some of this early mapping, I find it's really quite intriguing, and it's something we'll return to when I show you some images later. This first map here of from the late 19th century looks a bit stylized and a bit stark, but there are some features in here that we'll start to see echoed in other mapping as well. Some of these accurate features that we can see here. Sorry, can you see my cursor okay? I'm assuming you can. You'll shout out if you can't. And on this 1934 map here, you can see again these arcuate forms that have been drawn here. And this looks, well, when you see some other slides, you know, the powers of observation from these early scientists are really quite remarkable. And we'll see a few more here contained in these early books about Mercury. The Patrick Moore book was one of the first books I ever owned as a boy, and it really fascinated me, just all about this planet and the mapping that we see again. And we're starting to see some really distinctive features here. This circular feature and this again arcuate ridge, again echoed in several of these early images. And when you think how difficult it is to see Mercury and the capabilities of the early telescopes, you know, the observation powers of these early scientists are really quite admirable, and it's something I really quite admire about scientists of the Victorian and early 20th century. Didn't have the technology and the instruments we have, but they did have their eyes, and they were very good observers. So a few significant events. Well, 1631, first telescope examination of Mercury, and then the first transit seen. But it's in the 60s where we really start to get some interesting analysis from the radar signals from the Soviets, who were so dominant in the early 60s in many areas. And also then some radar recognizing the strange rotational characteristics of Mercury. But it wasn't until Mariner 10 where we started to get some real photographs during some flybys. And then subsequent to that, there's been quite a lull in activity, but some more radar in the 90s finding ice, and that attracted a lot of attention and interest, water ice. So of course, MESSENGER, that's the real significant explorer that we've been enjoying the data from that. And then 2018, Bepi Colombo launched and is on the way, and I'll mention that right at the end of the talk as well. So let's take a look at some of the images from Mariner 10. Well, I think this is a brilliant composite image. It really just captures the nature of Mercury. Unfortunately, it probably did for Mercury as a point of interest after Mariner 10, because it looks so dull and uninteresting. That focus then went to Venus and particularly to Mars, which I think is a bit unfortunate, but I'm glad that we got subsequent probes to it. But this was launched in March 73. It's quite an interesting exhibition or exploration because it was the first to use flybys to use a gravitational pull of one planet to get to another. So it flew by Venus, and then several flybys of Mercury to take these images. So as I said, our first mission to visit 2 planets. So a range of instruments there you can see that undertook some interesting analysis, not a huge amount of data, but did start to and some slight detection of perhaps helium in the atmosphere. But other than that, it was really the images that really caught attention. So these are some of the images of Mercury that from Mariner 10. So some really good quality images, particularly of the time, and that these are in flyby, not in orbit. And again, showing the series of a very cratered planet, very significant bombardment, and we'll look at some of these features a little bit later in a bit more detail. But these are the images from Mariner 10. And that was pretty much it until MESSENGER was launched. And I want to go through some of the data that MESSENGER brought back. This is the NASA patch. I always quite like the NASA patches that they have for the missions. And we'll take a look at some of the data. But here's some stats. 8 billion miles traveled. It's quite an impressive. Over 1,200 days in orbit around Mercury, 35 million shots. I mean, goodness, how do you sift through that? Thought, and 250,000 images. So really quite an impressive mission if you look at this data. Now, I want to play you a video here. It's longer than you might normally expect. It's about 8 minutes. But I think it's a really very good video in that it covers a lot of what I would call the background and the groundwork about Mercury. It gives the context of what we'll be talking about, gives some insights into that. And then it allows me to actually focus on some of the areas that I think give some insights into the nature of the planet and its evolution. So if you can't hear this, you should be able to hear the sound, but give me a shout out if you can't. We'll just let this run through.
Mercury. It is of course the solar system's closest planet to the Sun. Stick with me on this video and you'll learn everything you need to know about Mercury. Everything I'll show you today will be actual picture or video images of Mercury. We'll be talking about the orbit and rotation of Mercury, its physical characteristics, its surface conditions, and the magnetic field and magnetosphere of the planet. Now when you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the Sun and this giant rock just floating in space. You wouldn't be too far wrong with that, but it is much more interesting than what you may first think. For example, when I look at Mercury I do think of our moon, but Mercury actually is visually more appealing than our moon. Look at it in its true colour. The first thing that I notice is that it actually does have a colour. It's not just different shades of grey. And what else? Well, did you know for example that Mercury consists of approximately 70% metallic and 30% silicate materials? Because of this, Mercury's density is the second highest in the solar system at 5.427 grams per centimeter cubed, only slightly less than the planet with the greatest density, that of Earth, at 5.515 grams per centimeter cubed. If Mercury happened to be the same size as Earth, that would mean it would have pretty much the same gravitational pull as its surface. But being the size that it is, its surface gravity is only 3.7 meters per second squared. If you would compare it to Earth, it would look something like this. This means the surface gravity of Mercury is only slightly less than what it is on Mars. And considering Mars is a much bigger planet, that just says something about the density of Mercury. Before we leave the subject of Mercury and its size, I want to show you one last comparison, that of Ganymede and Titan against Mercury. Now Ganymede is the solar system's biggest moon and also the biggest moon of Jupiter, while Titan is Saturn's biggest moon and is the second biggest moon in the solar system. These two giant moons are bigger than Mercury as you can see here, but their masses are less. If you look closely at Mercury's surface, you'll see its appearance is similar to that of the moon. It shows extensive Mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. But it obviously was geologically active at one point, because one of the distinctive features of Mercury's surface is the presence of many narrow ridges, extending up to several hundred kilometers in length. It is believed that these were formed as Mercury's core and mantle cooled and contracted over time when the crust had already solidified. And one distinctive thing you'll notice about Mercury is this huge crater on its surface, Caloris Basin, with a diameter of 1,550 kilometers. The impact that created Caloris Basin was so powerful it caused lava eruptions and left a concentric ring over 2 kilometers tall surrounding the impact crater. At the antipode of the Caloris Basin is a large region of unusual hilly terrain known as the Weird Terrain. If you would compare it to the rest of Mercury, you would see why it would have this name. So, what's it like on the surface of Mercury? Well, to start with, the surface temperature is hugely different all over. It can range from minus 173 degrees centigrade to over 400 degrees centigrade. It never rises above minus 93 degrees at the pole because there's no atmosphere retaining the heat, and so there's quite a big difference between the equator and the poles. But it's also due to its orbit and rotation, which we'll get back to later. The subsolar point reaches about 400 degrees. while on the dark side of the planet the temperatures average minus 163 degrees. Because Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time, it's not able to retain any of the heat it gets from being so close to the sun, which is why the dark side of the planet is so much colder than the side facing the sun. Mercury though does have an exosphere, which is like a very thin atmosphere-like volume surrounding the planet where molecules are gravitationally bound to that planet. But the density is so low that it can't behave as a gas because these molecules don't collide with each other. In this picture you can see proof of the exosphere. When solar winds hit the planet, they rip off certain atoms out of the exosphere, and what's left is this trail of atoms going into space. We call this the planet's tail, and every planet has this to a certain extent. Earth does have an exosphere, but it's 600 kilometers above the surface. It's really the point where space and the atmosphere meet. Now in the case of Mercury, this exosphere is not at all stable. Atoms are continuously lost and replenished from a variety of sources. Very recently, NASA's been able to confirm that craters at the North Pole contain water ice. Mercury also has something which Mars lacks, an actual magnetosphere or a magnetic field all around the planet. Now it is only about 1.1% as strong as Earth's, but it's still strong enough to deflect a lot of the solar wind around the planet. And now finally we're going to get to one of the things which I find the most interesting about Mercury, its orbit and its rotation. Mercury has the most eccentric orbits of all the planets, with its distance from the Sun ranging from 46 million kilometers to 70 million kilometers. Now this is something a bit hard to imagine. Mercury takes about 88 Earth days to complete an orbit around the Sun. It also has a 3-2 spin-orbit resonance of the planet's rotation around its axis. This means it spins 3 times around its axis for every 2 times that it orbits around the Sun. So although it takes about 59 Earth days for Mercury to rotate on its axis, but with this 3-2 orbital resonance, actually standing on Mercury, it would appear that one day from sunrise to sunrise is 2 Mercurian years. Standing on Mercury, that would look something like this. You see the sun rise quite fast, and then as it approaches midday, it slows down and even starts going backwards before continuing on again to sunset. As you can see, that took a whole year, which means a nighttime on Mercury also takes a year. The sun starts going backwards in the sky because approximately 4 Earth days before perihelion, the speed in which Mercury rotates around its orbit equals the speed in which it's rotating, so that the sun's apparent motion stays stationary. At perihelion itself, Mercury's orbital speed exceeds its rotational speed, so to a person actually standing on Mercury, the sun appears to move backwards. 4 days after perihelion, the sun's normal motion resumes. You can see this even clearer from a top-down perspective of Mercury on one of its poles. Twice a day, the sun seems to pause and then continue on again. Something else to note about Mercury's orbit is it's inclined by 7 degrees to the plane of Earth's orbit. As a result of this, we can only see Mercury in front of the sun when it's directly between us on Earth and the sun itself. And because its orbit is inclined by 7 degrees, this only happens about once every 7 years. And finally, about the rotation of Mercury, its axial tilt is almost 0, with the best measured value as low as 0.027 degrees. This is even smaller than that of Jupiter, which has been measured at 3.1 degrees. And finally, do you want to see Earth from Mercury? Well, here we are, just a couple of pixels across. This picture was taken from the Messenger probe a couple of years ago, and every single one of us was in this picture. Well, thank you so much for watching this video. I hope you learned something today about Mercury and that it seems more interesting to you now than when you started this video. I'm really grateful as well for everyone who watched the Mars video on my channel.
Well, I hope you enjoyed that. I have to watch that graphic on the rotation and the sun moving several times. It's really quite intriguing, just to try to get your head around that. In fact, I think the whole aspects of the orbit and rotational characteristics of Mercury and Venus is probably worthy of a separate study and talk. It's really quite intriguing. So what I want to do is just look at some of the key areas that were covered in that video in a little bit more detail. So as was said, the core of Mercury relative to its size is really quite significant. This graphic here gives you some idea of just that relative dimension, and that it's a metal core. It gives us some indication to the origins of Mercury, which I'll come back to. But it says, as it says here, liquid iron core about 3/4 of its radius, so far more significant than on Earth, and I'll come back to that too. The topography of Mercury, well, we saw this. I'm just going to play this again, just because I think it's quite a nice image showing the characteristics of Mercury. Oops, no, I won't. Let's go back. There we go. So you can see it's really quite distinct in terms of the lows and the highs in this false color image. Quite distinctive terrains across the planet as a whole. And these are areas that we'll look at in some detail from a geochemical point of view. So here's that Chloris basin that was highlighted. The false color images shows areas of volcanism. I want to look at that in more detail. And some aspects of volcanism that we do see on Mercury are so-called shield volcanoes. So you may have heard this term in relation to Hawaii and other types of volcanoes. It's really this broad doming effect rather than a traditional sort of, what should we call it, sort of cone shape of a volcano. But what is interesting here is this so-called kidney shape within the depression, indicating some explosion of some sort that has occurred within the basin itself, within the crater itself. We'll have a look at some more of those features in a moment. But here's another crater on the south polar region. Black areas, again, false color, permanently in shadow. And it's in these areas that we start to see water ice developing as well. And it was here that this was some of the first evidence for water ice that was determined. And it's quite something to think that a planet so close to the sun and being irradiated so heavily still has water ice in it. And here we see again northern polar region, the yellow areas in terms of again false color, but showing areas of water ice, so permanent shadow, and the red shows the permanent shadow areas in general. So there's quite a significant area of the planet that is in permanent shadow, which I think is quite interesting. And some of these features are quite fascinating. Here's a crater. And if we just zoom in on this small section here, we start to see some hollows, and these oddly shaped hollows. Again, you can see here, and there's some idea on depths, 20 meters, 25 meters, and so on. And not very large, just kilometer across, something of that nature. And these are evidence of explosive reactions, probably due to volatiles exploding or being released explosively from these crater areas. And if we look into these in some more detail, we find that they're really quite. This is a small area here, expanded 5 kilometer scale here. There's quite a lot of irregular shapes. It's not sort of volcanic eruption type shapes, and it's certainly not impact crater type shapes. So these are evidence of volatiles being lost from the surface of Mercury due to its harsh environment. And as we'll see, that volatile loss is related to its proximity to the sun. So here's a good example of the northern plains latitude, very smooth area here. So clearly younger in terms of its surface than the heavily cratered area, but still really formed quite early in the evolution of the planet after the significant bombardment of the planet. But this is, again, it's significant, about 6% of the planet in terms of volcanic eruptions or lava flows. So let's take a look at some of these tectonics and the ridges. Now, you might have heard the expression of Mercury being the incredible shrinking planet. And that's due to the cooling of the core. And as the core cools, so the crust starts to crack and contract. And as a consequence, this creates these significant ridges. And you can see this ridge crosses this crater. So again, you get a relative stratigraphy or timing of these events. And this is the high terrain, this is the lower terrain. And we see this quite significantly in some of these ridges that we see here. Now, you might see this inverted, you might see this as a crevasse, but it's not. This is the shadow area created by a ridge of about a mile high. And there are lots of these around the planet, and you can see it breaching that crater there, again, given its relative dating again. And these so-called grabens or linear troughs create these fault scarps. And these are the features that when I was looking at those early maps, I wanted to relate to you. And I just think it's quite phenomenal that those early telescopes and those early scientists could actually visually see these scarp quite distinctly and map them, even though their telescopes are relatively modest. So I think that's quite remarkable. And it's these scarps that form as the planet cools and contracts, and some areas contract more than others, and so we get these scarps formed, as I say, up to a mile high. And this again, another false color image, but shows the relative heights up to 10 kilometers high in the reds and the lower basins as well. Now, most planets are not tectonically active, certainly not like the Earth, but it's this contraction and this cooling of the core is still continuing today. And there's some contrast between the Mariner data from the 70s and the Messenger data. There's a bit of debate in the literature as to the significance of the extent of the difference. Some data suggests that the planet's contracted by about 2 kilometers in size. Others suggest more to 10 kilometers in size. To be honest, I think what's just really significant is that contraction is being observed as a difference within our lifetime, which I think is, geologically speaking, that is very, very rapid. And so we're still seeing faults form today, these more ridges form today, and it's suggested that as that cooling is still continuing, we're likely to have Mercury quakes as well. So here's an impact basin, very smooth floors, and just as you'd expect, you know, the impact basins filled with basalt typically, but lava, and we can look at those in more detail as well. And here's just another example of strange features, impact craters, but still some strange features which actually look more like volcanic vents. And here's some good striations, as you typically see in volcanoes on Earth, of the features of following eruptions as well. So let's just go through a geological history, if you will, of Mercury. Well, formed 4.6 billion years ago, obviously heavily bombarded by asteroids and comets, which came to an end about 3.8 billion years ago. So between that time and about 3.5 billion years ago, there were significant lava eruptions pouring out, forming those smooth terrain, that smooth area that we've seen in earlier of the images. But that came to an end really very quickly, probably only lasted, well, less than 1 billion years. And I think that's really quite intriguing to think that, you know, for a planet that is so heavily cratered, clearly heavily bombarded, and that we've got these plains of basalt and volcanism that are so ancient that really have hardly suffered any volcanism at all, or any bombardment at all. So really quite intriguing stratigraphy there. And here's a contrast between Earth and Mercury. Relative sizes in the bottom box here. But what is really interesting is very thin crust, as is so typical. The mantle, a solid iron sulfide layer, which is quite intriguing, determined largely through geophysics. and liquid core and a solid inner core. And clearly this is continuing to cool and becoming more and more solid, and this will change over time as well. But you'll notice that the whole core is so dominant, right, compared to, for the planet's interior, compared to Earth. And that impacts on, and we can determine a lot of that from the geochemistry of the planet and the surrounding exosphere. And this is really where I want to spend a little bit of time. Now, clearly, when we're analyzing rocks in the laboratory, we bring them in, we subject them to, it could be X-rays, for example, and we determine from the excitation and the wavelengths of the X-rays that we know which elements are present in the rock. Now that's useful in itself, but what we really want to do on Earth is actually determine the concentration of those elements. And to do that, we analyze our sample and we compare the results with the analysis of key standards. So we can equate the size of the peak in the sample to the size of a peak at given concentrations in our standards. And through that, we can determine the concentration. You clearly can't do that from orbit, but what we can do are scans using gamma rays, X-rays, any technique that will excite elements on in the lithosphere of the planet. And we can ratio those elements. Now, you'll see in the coming data, we normalize or ratio this to silicon. And the reason for doing that is, firstly, we can't do absolute concentrations. But we do know from analysis that silica is pretty uniform in its concentration, because we see the size of the peaks being comparable throughout the surface of the planet. So whilst this is not a quantitative technique, it certainly gives us an indication that the concentration of silica will vary very little, but the concentration, for example, of magnesium will actually be quite significant. So it's a very good indication of differences. And I want to run through some of those areas that were highlighted in the video. It was found that calcium emissions in the exosphere were detected, and it's based on 4 years of observations, and we can see this quite clearly. It's typically in the sort of terminator or perimeter here, where there's dawn and dusk on the planet. And if we start to look at this, we've got the calcium observations and the sodium observations. Here's some scale here as well. We'll come back to sodium in a minute. But the calcium observations were quite interesting, because given that we've got analysis over a period of time, it was possible to determine that the calcium in the exosphere varied throughout the year, but it varied in a consistent manner. And it was always when Mercury passed closest to the sun. So the obvious conclusion then would be, well, it's the solar wind and the intensity of the radiation that's creating that. But on inspection, it was found that it was not so much to do with the excitation of the radiation from the sun, but it was more through Mercury passing through a dust stream from a comet. And the dust of this comet bombards the planet, and it's that creates the calcium that's been emitted from the planet, who's been thrown off by the dust particles. So it's been ablated, if you like, from the planet, which I thought was quite intriguing and not something that one might expect. Sodium, this is probably the area that's been studied most significantly because it's perhaps more readily to detect and it's more frequent. But again, we see this variation over the orbit of Mercury, and again, when it's closest to the sun, we see most of that. What is quite intriguing is this observation here that if you're on the night side, it would look like an orange glow, a bit like you see from a city in the distance. But the sodium tail here is quite interesting. Again, we see the length of that tail varies between the two flybys. And it's because of the proximity to the sun and due to the the irradiation of the sun exciting the surface of the planet, that we see this variation. So that's a bit about the exosphere. Let's take a look at the actual rocks on the planet, or the surface of the planet. And again, we're using silicon as the basis of these ratios. So Caloris Basin, the blue, and looking at the top left, the magnesium silicon ratio. And quite distinctly, you can see this high magnesium area. And if we look at sulfur, well, we see an equally high distribution, quite a distinct area of elevation. Doesn't quite overlap the magnesium, but it's still quite significant. And likewise with iron. Now, iron is obviously a denser element, and Mercury needs to be close to the sun to get sufficient excitation to start to detect iron. So iron detection is a bit more complex and not so easily on various orbits to obtain. But again, we've seen an overlap with the magnesium, but not a direct correlation. And this so-called fast neutron scatter, again, that's looking at areas of heavy element excitation by the faster neutrons. And again, we get this overlap with the magnesium. So the suggestion is that if you get a high impact that penetrates the planet to some significant depth, it goes through the crust. The bombardment will go through the crust and excavate some of the mantle material. Now, we know from comparisons with Earth that mantle material is much more enriched in magnesium and other compounds as well. And we saw that iron sulfide layer from that early section of Mercury. And whilst the correlation isn't complete, again, we start to see this evidence that of sulfur and iron coming to the surface much more in this high impact area, suggesting that the crust is thin there in terms of comparison with the rest of the planet. That was perhaps more mantle material there. And this is indicative of an ancient impact area, but one that's been degraded. It's not obvious from a topographic sense, but it is quite distinct from a geochemical sense. And so we start to see what are called distinct geochemical terrains, as we see on this close-up here. And we also get it with aluminium. Now, aluminium, in contrast to magnesium, is more common in minerals that are on the crust rather than the mantle. And we can start to see it again in this area where the Caloris Basin is. It may have low magnesium and silicon, but it does have high aluminium silicon ratios. And there are a number of elements that this has been done to, the number of ratios that this has been analyzed. And we'll see that actually this gives a quite distinct characteristic to Mercury. Now, I'll just take you through this. So here's a graph of aluminium silicon ratios against magnesium silicon. Here we have the lunar soils in the little boxes, earth basalts, earth mantle rocks, quite distinct. So surface terrain, mantle rocks, deeper terrain. Mars, again, broadly following a comparable gradient on the line, and Mercury here in this intermediate area. So what we can say is that it's comparable in terms of this gradient, this spectrum, if you will, of the ratios compared to Earth, but equally it's quite distinct. It has its own distinct ratios that don't tie in with Earth basalts and don't tie in exactly with Earth mantle rocks as well. We'll come back to that in a moment. So potassium's intriguing. We find potassium quite low at the poles, but high at the low at the equator, but high at the poles. And it's one of the volatile elements, so like sodium, a volatile element, very depleted on the moon, but clearly not so on Mercury, which is quite intriguing. And what we find in these areas, this high potassium areas, the low in magnesium, silicon, calcium, sulfur ratios, but high in sodium and chlorine. So this implies that these volatile elements are concentrating in this area, but not on the equator. And if we look at compare potassium again with thorium, now thorium is quite uniform over the surface of Mercury. We find the planets, Mercury, Venus, Earth, Mars, have quite distinct ratios of potassium to thorium. And we can see this on this graph. So again, the moon, very different, very distinct line here because the potassium has been depleted over time. This line here shows a good gradient with the planetary ratios. So we've got here Mars, Mercury in the red here, a bit on terrestrial crust. The Venus lander is not enough data there to do much with, and Martian meteorites also on this gradient. So quite consistent within that planetary bodies. Okay, let's pull all this together then. It shows that, well, feldspars are the main mineral that host potassium and sodium. And it gives an indication of temperatures that Mercury has experienced in the past. Now, potassium is more volatile than thorium. And if potassium was depleted, we'd expect really high temperatures in the past that would have just boiled the potassium into space. But that's not the case. That's not what we see. We see a high ratio of potassium to thorium, which is similar to the rocky planets, which we've just seen in that graph. So it's not depleted in volatiles, which is perhaps counterintuitive because you'd think being so close to the sun, Mercury would have been really subject to really intense, extreme heating, but it doesn't look like that's the case. So from these early analyses and these early indications, we can get some indications of Mercury's formation. It rules out some of the models that have been suggested, such that Mercury lost most of its mass in a collision with a similar sized object, or as used to be very strongly thought, it's so close to the sun that the sun and the radiation just stripped away the planet's outer layers, effectively just eroded the planet. That clearly wouldn't be the case, because if that were the case, we wouldn't see the potassium-thorium ratio that we do. So this lends itself to the fact that Mercury formed by the accretion of conditoric-like meteorite material, which I think is quite interesting. I'll cover graphics of the two options there. So it gives you an indication how we can start to get some insights, even from relatively empirical and semi-quantitative data, on the geochemical characteristics and geological evolution of Mercury, going right back to how it might have formed and ruling out some of the other options. So there's still some data to be analyzed from MESSENGER, still some papers to come out yet, I'm sure, but that's a summary of where we are at the moment. Bepi Colombo launched in 2018, arrives Mercury in 2025. An orbit is two spacecraft, an orbited spacecraft, which are illustrated here. And this is going to be really quite intriguing, because we'll get a complete map of Mercury in different wavelengths. We'll get the mineralogy, geochemistry as well, to build on what we've already known, and determine more whether the interior of the planet is molten. So we'll get some geophysics on this as well. And it's obviously using gravitational pulls to bring it into orbit. First pass of Venus, 2020, an image there, and this first image of Mercury's northern hemisphere last year as it flew past for a gravitational assist. So it's going to be some years yet before we get more data, so we can further understand the geochemistry and mineralogy of Mercury, and I'm really looking forward to that, and to some more data coming out of MESSENGER. And with that, I'll close. Thank you very much. I bring my own audience just in case.
Thank you very much, Keith. That was an excellent presentation. I will hand over to Chris now, who's got hopefully some questions there, if he's even there. Is he there, Chris?
Yes, I'm just unmuting now and sorting out the camera. Yeah, thanks for the presentation, Keith. Those images are stunning. I know some of them are enhanced, but still looking absolutely spectacular. Thank you very much. So if anybody has any questions, please chuck them into the Q&A box. I do have three, whilst waiting for other people to ask questions. I've got three from Rich. So the first one was, how big was the object that caused the Caloris crater?
There's a good question. I haven't seen any data suggested on that. It's as you can see, it's a significant basin. I think, was it 1,500 kilometers across from memory there, but I haven't seen any estimates on the size of that. But I think what is it's clearly very significant, because as we saw in that video, it's not just created that impact crater, but it's actually created a shock zone throughout the planet onto the sort of antipole of that. But no, I'm sorry, I can't answer that. I don't know. It's a straight answer.
Cool. All right. Thank you very much. How voluminous is the water in terms of planet area and with reference to water volumes on Earth?
Yeah. I have seen some suggestions. I haven't seen that quantified as such, but in terms of respect to Earth, but in terms of the area that's always in shadow on Mercury, what was that, 6%? And it's not, and water ice isn't present in all that areas. Really quite modest sum. So it will be a fraction of a fraction compared to Earth. I think what will be interesting is comparing it to Mars. And looking at the evolution of Mars and water having been on Mars, and seeing water ice in the poles there, I think that will be an interesting comparison there. But yeah, I don't even know if anybody's done that calculation, but clearly it's going to be a very modest comparator.
Cool. So last question for Rich. So if anybody else has any questions, then please give us a shout. Obviously, aside from the stunning imagery that you've just shown us, what do you think is the most fascinating feature of Mercury?
Thanks. Yeah, well, I probably, I think what I really like to see is just how we've been able to use even those geochemical ratios rather than absolute concentrations to identify and support the topographic images, but those areas that are of high magnesium areas, which don't have any significant topographic features that you could easily correlate with that, we can still find evidence of former impacts that are now being eroded away, that have really had a significant impact on the the geochemical and geological evolution of the planet. So we can identify impact basins and impact areas, even if there aren't any topographic features. And I think that's particularly intriguing with Mercury, because it's so many of the features on it are so old. There's very little in the way of impact on those smooth basalt plains. I'm saying basalt, I'm assuming it's basalt, it usually is. So I find that intriguing, and yet we can still identify these features through the geochemistry and the analysis. So I really find that intriguing, and actually just trying to get my head around that orbit and the rotation and that 3-2 spin. I just find that really quite fascinating, and it's something I'd like to look at a little bit more, actually, in terms of just trying to understand how that might have come about, and likewise with Venus. So yeah, I think it's a fascinating planet. Sorry, go ahead, Chris.
Yeah, no, sorry, I interrupted you. I do apologize. Sorry, that actually sort of leads us into another question which Mick has posted. How did Mercury end up in such an elliptical orbit?
Yeah, exactly. There's a question. I think that's worthy of a further investigation, because as I started to do some research for this presentation, it's quite evident that whilst this has been defined and recognized in quite detail now, it's still curious how that has happened, and likewise with Venus as well. And I haven't seen any robust hypotheses as to how that has been evolved, how that evolved, and why that evolved, and yet Earth didn't really experience that, and for Mercury to have virtually no tilt on its axis as well. I mean, I think that's quite intriguing too. So yeah, it's a good question. It's not one I have an answer to, and it's not one I've seen really resolved in the literature, but I think it's one, yeah, that is certainly worthy of perhaps another talk in the future to understand that.
Something for further Google investigations. Thanks so much. So that's all the questions that we've got at the moment. If anybody else has any more, we might be able to find time for it right at the very end. But at the moment, that's everything. And as I said before, thanks so much for stepping in and for an excellent presentation. I'll hand you back to Rich.
Thanks.
Thank you for that, Chris. That was excellent work, mate. Keith, thank you very much for a really a stunning presentation. I think I agree with Chris totally that the slide images were great, and and the information that you presented was very good, and really helped your presentation. And I liked your inclusion of extra text onto some of the slides for our YouTube viewers, because we do actually get quite a few people watching it via YouTube, so they can just pause it and read the more fully the information. So thanks very much for that, and also thanks very much for turning up at pretty short notice, really, and giving us an excellent presentation. It rather dragged us out of a bit of a mire. As I said earlier, you're definitely a savior of the bacon, mate, so thank you. It's now we've got a little present to thank you here. It's a Sigma tumbler, and I'm hoping to get that in the image, so that's by means of a thank you for a really excellent presentation. And thank you very much, Keith.
That's really kind of you. Thank you very much.
Give us your address, we'll get that sent out to you, and thank you very much.
I've got just the liquid to fill it with.
Yes, well, it's you just need one of Scotland's finest single malts or something, mate. Anyway, thank you very much, Keith. It's a great presentation, and thank you very much. We'll go to our tea break now for 10-15 minutes and return with Stuart's Space News. So over to you, Mick, with the intermission slides. Hello and welcome to the second half of this evening's presentation. We've got Stuart's Space News, and I'll follow that up with a bit of club news with information on the AGM and July meetings and a few other things that we want to let you know about. So with no further ado, I'll hand over to Stuart for his stuff. Thanks, Stuart.
Right. Good evening, everyone. Welcome to Space News.
That's displaying great, mate.
Okay. Right. I've picked a few things out of what's happened over the last month. Artemis is still having its problems. Axiom's done its first successful commercial launch, and China's launched another observation satellite to join its previous two. SpaceX launched a clandestine spy satellite, and the farthest object in the known universe has been discovered. There's position on the James Webb Space Telescope, UFO reports, for those that believe in it, and Russia's robotic moon lander. The European Union has pulled out of part of that. And the French court revoked SpaceX's Starlink internet license. So first, NASA's Artemis 1 space launch system, mega rocket and its Orion spacecraft was rolled out onto its base 39B at the Kennedy Space Center in Florida on the 1st of April in preparation to commence 3 days fueling test, which was called the wet dress rehearsal. On the 2nd, if I can get this, on the 2nd of April, it was struck by lightning and such. However, there's no damage done and technicians worked through the critical test. So if I then go that shows you the protection from lightning by 3 towers and a catenary wire structure. It diverts strikes to the ground from the booster. This had been upgraded since the days of the shuttle. The first 3 lightning strikes were relatively low power, but the 4th, which hit Tower 1 of the system, was more powerful, and it was the strongest seen since the new lighting protection system was installed. It hit the catenary wire that runs between the 3 towers. The system apparently is reported to perform extremely well. The new system has an array of sensors both on the ground and on the mobile launcher, which help to determine the rocket's condition after nearby lightning strikes, which is hopeful to prevent delays. However, on pad 39A was SpaceX Falcon 9 rocket, which was scheduled to launch 4 private astronauts to the ISS on the 6th of April for the AX-1 mission for the company Axiom Space, which had been delayed from the 3rd of April because of Artemis delays and several technical issues, twice failed efforts to load propellant into the SLS tanks. And the mission team initially delayed and then aborted the test to accommodate the launch of AX-1, which launched on the 8th of April. The plan was then to resume the wet dress rehearsal on the 11th of April, but team members soon discovered a faulty valve in the Artemis 1 stack's mobile launch tower, a problem that pushed the beginning of the procedure back to the 12th of April and caused a modification to their test design procedure. And the team then decided to fuel up only the SLS core stage, not its upper stage as well. The test was then further terminated on the 16th of April after several failed attempts at fueling, and it was decided to roll the stack off the pad and back to the vehicle assembly building to replace faulty valve and address a leaky umbilical. So a bit of a sad story. NASA rolled it back on the 25th of April, and they stated on the 22nd of April that they expected the launch to be no earlier than August 2022. So that shows you the 2 NASA's space launch system at the right, at the back, and the Falcon 9 ready for the AX-1 mission. The idea was that the wet fueling test would go ahead before they launched the Axiom. However, that didn't happen. And that launched on the 8th of April. And that's the crew arrived there. So they arrived on the 9th and began a 10-day journey. The plan was a 10-day journey. It was to include 8 days aboard the ISS, during which time the crew would carry out various experiments for Axiom Space. And it was the first major step toward realizing its own commercial space station in low Earth orbit, which was also the first of its kind, first commercial. Axiom Space was formed in order to build the next commercial space station, and AX-1 is a precursor mission to build that station. However, on the 19th of April, United Press Internal reported that the AX-1 private astronauts aboard the International Space Station would stay in space a little longer because of poor weather in the area of the Atlantic Ocean where their capsule was to splash down. And then weather officials, together with Axiom and NASA and SpaceX, worked to determine when they could safely bring the crew home. They'd already done 12 days in space, and they eventually came back on the 25th of April after a 17-day flight. And that's them there. So that was quite a success, an extended flight, but it was a success. This is the third of China's Long March satellite launches, and that was on the 7th of April from the Jiuquan Satellite Launch Center in northwest China. And this is Gaofen 3, version 3. And it was launched by a Long March 4C rocket and entered the planned orbit successfully. The satellite will be networked with the orbiting Gaofen 3, 1 and 2 satellites to form a land-sea radar satellite constellation and capture reliable, stable synthetic aperture radar images. And these images will provide a 1 meter resolution together with a 1-day revisit period, thereby improving the monitoring capability of China's land-sea radar satellites. It will serve the fields of marine disaster prevention and mitigation, dynamic marine environment monitoring, marine research, environmental protection, water conservancy, agriculture, and meteorology, while helping to safeguard maritime rights and interests. The launch marks the 414th mission for the Long March series carrier rockets. Now, if you notice there's bits of white flakes coming off the rocket. Now, previously, I read that was tiles coming off, but I've since found out that is, in fact, fragments of ice, because the supercooled oxygen and hydrogen, which is stored for its fuel, while it's sitting on the pad, causes ice to form on the outside of the rocket. The vibration during launch causes it all to fall off. And if I show you, if I can, there's a little bit more. You'll see again, you'll see the flakes of ice coming off the rocket. I didn't understand why it was reported as being tiled, because I would have thought it'd been rather dangerous, in fact. We'll get another shot from a lower angle in a minute. Yeah. And again, you'll see the tiles coming off. The ice coming off. And then SpaceX launched a clandestine spy satellite on the 17th of April. And this was for the National Reconnaissance Office. And the rocket returned back to base within 8 minutes. I think it was 8 minutes, 17 seconds. The two-stage rocket carrying the NRL-85 spacecraft lifted off from California base, and the two stages separated about 2.5 minutes later. The first stage headed back to Earth, and as I said, making a vertical touchdown, the same base, about 88 minutes and a few seconds later. SpaceX ended its live webcast on the launch just after the Falcon 9 landed at the NRA's request due to mission's classified nature. So there's no information on what it was all about, but it's obviously shows that they can launch a satellite within about 8 minutes from Earth. And if I just show you the next one, oops. What I'll do is I'll just show you the launch, and then the recover. I'll head back to the camera's attached to the rocket, so you actually just see the tail of it going up. And as soon as you get to see you see it there. I'll try now just to do the recovery. That's it. That's all within 8 minutes. I think it was 16 seconds there that it did that, which is quite impressive, really. Now, the farthest object in the known universe. Harvard astrophysicist Avi Loeb stated on the 7th of April that at Harvard they discovered the farthest astronomical object yet observed. They believe this object is a galaxy, and if so, it's the most distant one currently known. The object carries the label HD1, and it lies 13.5 billion light years away. That's up there. I'll just show the, and from you can see there, you see where the newly identified farthest galaxy is. The age places the collection of stars HD1 between a time of total darkness. About 14 million years ago, the universe was a blank state devoid of any stars or galaxies, and one of just burgeoning lights as clumps of dust and gas were growing into their cosmic destinies. The first galaxies formed about 100 million years after the Big Bang. They were a millionth of the mass of the Milky Way and much denser. Study researchers and Harvard astrophysicist Avi Loeb told Live Science in an email. One way to think of them is as the building blocks in the construction project of present-day galaxies like the Milky Way. Measurement of a new galaxy from the early universe, HD1, have led to it being characterized as the farthest, youngest, most distant galaxy ever seen. And known as HD1 is thought to be a redshift of 13.27, a time just 330 million years after the Big Bang, and a distance of 33 billion light years away. But the properties of the candidate galaxy have not been spectroscopically confirmed, and some scientists state that without this key data, we should be highly skeptical. I don't know whether Professor Keith has got any view on that, if he's watching. The successful calling during its month-long calibration for deep space observations ensure that the observatory of James Webb Telescope will be able to probe cosmic objects in infrared light, according to a statement from NASA's Jet Propulsion Laboratory in California, which leads US work on the mid-infrared instrument, the MIRI. The operating temperature achieved is just above absolute zero. The telescope has been cooling ever since its launch on the 25th of December 2021, bringing it to the frigid temperatures necessary for MIRI to accurately detect infrared light, which manifests as heat. MIRI needs to be at a temperature of a little below 7 degrees Kelvin, which is equivalent to minus 447 degrees Fahrenheit or 266 degrees Celsius. The key challenge was achieving what is called the pinch point, during which the instrument dropped from a slightly higher temperature of 15 degrees Kelvin to the final super cold operating temperatures. This pinch point represents a transition zone during which the cryocooler, which is necessary to get Webb to its final temperature, had the least ability to remove heat. MRI's cool temperature are also required to overcome what scientists call dark current, or the electrical current created by vibrating atoms in the detectors. These small movements can generate false signals in the instrument's data, marring observations. Just to make such MIRI is behaving properly, the team plans more test images, stars and other objects to test its calibration and performance. Calibration is also ongoing on Webb's mirrors and 3 other instruments as the telescope team aims to finish its work by about June. On the 28th of April, alignment of NASA's James Webb Space Telescope was complete. After a full review, the observatory has been confirmed to be capable of capturing crisp, well-focused images with each of its 4 powerful onboard science instruments. And these are what they've produced. So obviously we should start getting some real exciting information and data back eventually when it's fully up and running. Encounters with UFOs have reportedly left Americans suffering from radiation burns, brain and nervous system damage, and even unaccounted for pregnancy, according to a massive database of US government reports recently made public through a Freedom of Information Act request. The database of documents includes more than 1,500 pages of UFO-related material from the Advanced Aerospace Threat Identification Program, AATIP, a secretive US Department of Defense program that ran from 2007 to 2012. Despite never being classified as secret or top secret, the AATIP only became known to the public in 2017 when a former program director resigned from the Pentagon. And released several now infamous videos of an unidentified aircraft, which you see there, on a seemingly impossible maneuvers to the media. Shortly after the AATIP's existence was revealed, the US outpost, which is the British Sun's office in America, filed a FOIA, request for information, but any and all documents related to the program. 4 years later, on the 5th of April, 2022, the US Defense Intelligence Agency honored the request by releasing more than 1,574 pages of material to the Sun. That's the newspaper. According to the Sun, the cache of documents includes reports on the biological effects of UFO sightings on humans, studies on advanced technologies such as invisibility cloaks, and plans for deep space exploration and colonization. Some portions of the documents were withheld in part for privacy and confidentiality concerns, the AATIP told the Sun. One standard document from the collection is a report titled Anomalous Acute and Subacute Field Effects on Human and Biological Tissues, dated March 2010. The report describes alleged injuries to human observers by anomalous advanced aerospace systems, some of which may be a threat to United States interests, according to the document. The report describes 42 cases from medical files and 300 unpublished cases where humans sustain injuries after alleged encounters with anomalous vehicles, which include UFOs. In some cases, humans showed burns, injuries, or other conditions related to electromagnetic radiation. The report said some of them appearing to have been inflicted by energy-related propulsion systems. The report also noted cases of brain damage, nerve damage, heart palpitations, and headaches related to anomalous vehicle encounters. It is unclear what kind of vetting process, if any, the AATIP used to investigate these alleged cases. The Sun has yet to share the full contents of the request reports. I thought that's quite interesting, but it depends on what you believe in, but how some of these injuries or effects have been caused. I would have thought they would need more investigation. But just on this one, I've got one or two of these. These pictures show the aircraft actually, someone's picking up the targets. The words at the bottom are picking up what the pilots are saying. Right. With that, it'd be interesting now that it's only just been released, whether people will investigate it a lot more to find out what it's all about. But I would have thought the Sun as a newspaper would have had a lot more to say. This shows Russia's Luna 25 moonlander, which is due to launch the summer this year. And the European Space Agency will discontinue its cooperation on Russia's Luna series of robotic moon missions. Announced that on the 13th of April. The development is part of ESA's effort to disentangle itself from a web of partnerships with Russia in the wake of the latter's invasion of neighbouring Ukraine. ESA's decision goes into effect immediately, and it is requested that the Pilot D landing camera to be taken off the Luna 25 mission, which is scheduled, mentioned later this year. And ESA's Director of Human and Robotics Exploration stated that removing the instrument will not have any effect on Russia's ability to conduct the mission, as it's not part of the operational system of the spacecraft. And Mr. Putin said on the, get the right date, which was the 12th of April, which was the day that Yuri Gagarin was the first spaceman in space, quoting that date that Russia will continue and succeed in their program. So there's obviously no problem there. And this is the next one, which is due to launch in 2025, Luna 27. This is an interesting one. The French court revoked SpaceX's Starlink internet license. The French court revoked SpaceX's Starlink internet license, citing monopolization concerns. The country's telecoms regulator will have to conduct a public consultation first before they can accept it, as it's the highest administrative court in France revoked the license to provide internet service in the country via the Starlink mega constellation, citing the monopolization concern due to the size and scale of the company's operation. And France's telecom regulator, ARCEP, awarded SpaceX the license in February 2021 without first conducting this consultation, the court determined. The court appeal was led by two environmental organizations that cited possible impacts of the mega constellation on the environment, including light pollution, space debris, and also human health. But the court, however, based its decision to revoke the license mostly on the argument that the nature of SpaceX's business, which includes rocket and satellite manufacturing, launch services, satellite operations, and telecommunication service, could distort the market and squeeze out competition, which at the end would negatively affect French consumers. That's probably should add Twitter there now, I suppose. Anyway, that's all space news for this week, and perhaps the aliens are getting here. Over to you.
Thanks very much, Stuart. That was a fact-filled space news as always, and interesting that NASA used the sun as its mouthpiece to put the stuff out about UFOs. Anyway, Stuart, thanks very much. That was a great
screen off there.
Thank you. Great. That's good. Hey, we've got a bit of club news now. As you'll know, the AGM is next month. There's been a bit of a change in plans for the AGM. What we've decided to do, or what's happened, is Jim Dunlop was unable to speak after the AGM as we planned. So Jim's moved to July. So that means that what we're going to do is swap places between the Soak and Jim Dunlop. So what we therefore decided was that we'd hold the AGM as an actual physical meeting at Lambride. So details will be going out about that, but that will be combined with a solar observing event. So hopefully the sun will shine, but you know, most probably we've set in motion the fact that it'll pour with rain, I would guess. But anyway, so here's hoping that will work well, and we'll just have the soak after the AGM. The paperwork will be going out for the AGM in the next few days, and we'd obviously be grateful if you could turn that around and get that back to myself actually as soon as possible. With I think we're planning a closing date, I think of either the 22nd or the 25th of May. But what we plan to do is a proxy voting system as we would have had for a virtual meeting. What we feel is that the proxy voting will allow everybody to vote, even those who don't actually turn up at the meeting. So we're keeping that plan going of issuing paperwork and asking for you to vote by proxy, but there will actually be a physical meeting which you can turn up at. And that leads me to the second thing, the survey that we're currently holding into how to format future meetings. We think as well that if we hold the AGM as a physical meeting, that will allow as many people as possible to voice their opinions on how we go forward with our main monthly meetings. So you know, by having a physical meeting, that should help with that sort of thing. That's that. The survey will run again for a couple more days. We've had a very good response to this, but if you haven't already responded, we would really appreciate if you venture an opinion, please, because that will help us to formulate the best way of taking the club forward in the future. We're also planning a slight revision to the newsletter. We had a meeting with Helen and Tim a week or so ago, and what we're planning to do is edit it using a software called MailChimp, which will produce a very contemporary looking newsletter, one that's easily able to be read on tablet and with mobile phones, smartphones. So what we're looking for though is a bit of help with this process, and we need people to join our editorial team to help us out a bit. What we'd be looking for is anybody with any sort of document writing knowledge, sort of how to use Word, PDF, that sort of thing, and also specifically if anybody's got any knowledge of how to edit using MailChimp, that would be a great thing as well. Now, that's it isn't a have to have. That would just be a great thing if you've got it. But most importantly, we just like volunteers to join the editorial team. If there's enough of us, it shouldn't be too onerous a thing to do, you know. So anyway, we need people to help us edit it, but also we need people to write articles for us. So if you've got any small article or even large article on with an astronomical sort of bias, that would be great, and we'd love to hear from you and have that so we could include it and include that in the newsletter. So I'm just sorry, I'm just fiddling around here, copying the link for the gathering into to put it into the chat. So there we go, and send that. So that's the link just gone into the chat for the gathering, which will be following this meeting about 2 or 3 minutes after this meeting. What Mick and myself will do is close this meeting down and get that link set up and running. So anyway, just to reiterate on the points I've made here, the AGM is next month. that's going to be a physical meeting, which will be combined with a soak. Jim Dunlop's meeting, talk and presentation will be moved from June to July, and the AGM paperwork will be going out in the next few days. We'd like you to complete that and get that returned as soon as possible. And if you haven't completed the survey, if you could, that would be great. Okay, with that, I'll say cheerio. Thanks very much for joining us tonight. And I've just had a note in chat from Mick saying, or from Helen actually saying, mention membership of the committee. It's yeah, if you'd like to join the committee, you'd be more than welcome. We've got quite a few tasks to do, and it's the more we can spread those tasks amongst people, the less onerous it becomes. So thanks for reminding me of that, Helen. That's very, very good of you. And so we'll, without further ado, we'll close this meeting and say thanks very much for joining us. We hope you've enjoyed it, and we'll look forward to seeing you in a few minutes in the members gathering. So over to you, Mick, with the closing slides.